Hi everyone, welcome back to another video. This week we're going to continue looking at trig identities or simplifying trig expressions. This week we're looking a little more in depth. We're going to add a few more ideas into the mix and kind of start to combine multiple ideas together. So as always, if you have questions, make sure that you are sending me private comments or you're asking your classmates via the discussions that we have in place. So before we get into a practice problem, I want to review a few core ideas that we're going to be implementing and just thinking about today. So the first one is the Pythagorean identity that we looked at last week, and that Pythagorean identity is similar to the Pythagorean theorem. It states that cosine squared of some value or angle theta plus sine squared of that same value, which we're calling theta, is equivalent to 1. So this is a Pythagorean theorem. It's like a squared plus b squared equals c squared, except we're using it on a unit circle and with sine and cosine. Now there's a couple variations we can use of this. So we can solve this for sine squared theta. If I solve it for sine squared theta, it's equivalent to 1 minus cosine squared theta. All we did there was subtract cosine squared theta. Or we can solve this for cosine squared theta. And if we solve it for cosine squared theta, well, we're going to subtract sine squared theta. So 1 minus sine squared theta. So what this does for us is it tells us something that is equivalent to sine squared theta and something that's equivalent to cosine squared theta, as well as something that's equivalent to 1. So we're going to see this in various forms through these practice problems. So that's the first idea we need to look at. There's two more actually, and the second one is defining tangent in terms of sine and cosine. So if we want to define what the tangent of an angle or theta is, that is equivalent to in SOHCAHTOA opposite over adjacent, but those are legs of a right triangle. If we want to define tangent in terms of trig ratios, well, tangent is equal to sine theta over cosine theta. So this is a big key idea. We can rewrite tangent in another form. And then the final one goes back to algebra. It's an expansion of a perfect square trinomial, or binomial, I should say. And if we have something of a plus b quantity squared, resist the urge to multiply this and just distribute actually, because we can't distribute exponents in that way. This is equivalent to a plus b times a plus b, which multiplies ba squared, plus 2 ab's when we multiply it, plus b squared. So this idea of expansion is going to come into play as well. So let's get into our first problem. There's going to be three. We'll do 3 different videos as well. So the first problem, we want to show that cosine theta plus sine theta quantity squared plus cosine theta minus sine theta quantity squared is equal to 2. So somewhere along the way, this is going to simplify down, probably through that Pythagorean identity that we just talked about. So with these sort of problems, don't get too hung up right away in worrying about what it equals. If we go through and simplify this down, most of the time, it will just reduce to be what we're hoping it to become. We know that this is equivalent to 2 because we're asked to show it. So we don't need to get too hung up on how this and this become 2 right away. We want to get hung up on when we've reduced this, done everything we can. If we're not seeing 2, then we need to start worrying. So let's start this out. First thing we're going to do is expand this out as much as we can. So when we take cosine theta plus sine theta and we square this, well, what that's equivalent to, we'll multiply this one out, is it's equivalent to cosine theta plus sine theta times itself. That's what it means to square something. So we're going to multiply this by itself. So cosine theta again plus sine theta. Doesn't matter what those variables are, if they're alpha, phi, alpha, beta. We'll use a lot of different Greek symbols just to represent angles. So when we multiply this out, we're actually distributing. So we distribute this cosine theta into the other set of parentheses. Some people call this FOIL. I just think about it as distributing. What we get is cosine theta times cosine theta. So we get a cosine theta squared, but recall that we notate this a little different and just say cosine squared theta. And then we have cosine theta plus sine theta multiplied together. So we have a cosine theta times a positive sine theta. I think I misspoke there. So there's our cosine theta distributed. Now we do the same thing and distribute the sine theta through into the other set of parentheses. So when we multiply sine theta by cosine theta, I'm just going to rewrite it like I had here already because it's equivalent through the commutative property of multiplication. So this is the same thing as cosine theta again times sine theta. And finally, when we distribute sine theta times sine theta, well, that's sine theta squared. But again, the way we notate that is a sine. I started writing cosine there. It's sine. Hopefully this remembers the size. It's sine squared theta. And then we can combine a cosine theta times sine theta plus another cosine theta sine theta. So this actually multiplies out to be cosine squared theta plus 2 of these cosine theta sine theta plus a sine squared theta. So there's our first or left term expanded out. Now, without showing all the work on this to expand the other one out, it's going to be almost identical, except when we start distributing this, instead of a cosine theta sine theta, we're going to have a negative cosine theta sine theta. So if we rewrite this in another color, let's use this green. If I expand this part out now, we're going to have plus another cosine squared theta, but this time because it's a difference of 2 squares, yes, it's a difference, we're going to have minus 2 cosine theta sine theta. And then finally, we're going to have another plus sine squared theta. So there's our right side multiplied out. So we still don't see the 2, we see some cosine squared sine squared. Now we get into reducing these and combining. So when we start combining this all the way across, what we're going to have is I have 2 cosine theta sine theta, that's positive, and then I have a negative 2 cosine theta sine theta. So these actually reduce or add to be 0. So when we write this all out now, what we have in the end is we have a cosine squared theta plus sine squared theta plus cosine squared theta plus sine squared theta. And using the Pythagorean identity, we see that cosine squared theta plus sine squared theta is equivalent to 1. Cosine squared theta plus sine squared theta again is equivalent to 1. So we have 1 plus 1, which is 2, and that's what we were trying to show this is equivalent to in the end. So no matter what angle I use here, if I use pi halves, if I use 3 pi halves, if I use negative pi sixths, no matter what I do with this, what angle I use, it will always come out to be 2. That's because some values reduce and we're left with Pythagorean identities in the end. So this is the first example. We multiplied out in this one, and the other ones we'll start introducing some other ideas. I hope this helped. We'll see you soon.